undergraduate students in the lab are all here because they must be here. Right, yes, okay. So I'm going to claim that this will be one of the first of a series of talks on explainable AI. And for people who don't know what explainable AI is, then I guess you have to attend the talks. Or you could try reading literature from last century. That would help too, because there's been a lot of work done on such. My colleagues have asked me for papers, and recent papers will be published soon on the Explainable AI Lab site. But today we have the pleasure of somebody I've worked with in Europe. So Andreas Holzinger, you see the affiliations here. I count as one of the leaders of explainable AI in Europe. We worked together. He put the end of the title on the last paper we worked at. It said something about explainable AI, the new 42. So everybody who remembers why 42 is the answer to the question. And that's where that reference comes from. In our own explainable AI lab, we work on two application areas that are largely driven by exposing sensitivities in legal reasoning and medical reasoning. So we are not aficionados or strong supporters of the simplest of all learning methods, which is deep learning, which is the virus that's caused the current AI pandemic. We're happy about the attention we get, but we think that that scratches the surface of modern AI. And sometimes the scratches are costly. But with that said, in this context, Andreas has been working on the relative development and application of explainable AI in a field which is one of those that's most highly sensitive. How many people have heard of GDPR? Okay, those who have not put up your hands. If you haven't heard of GDPR and you're interested in AI and explainability, you had better look it up. General Data Protection Regulation in the European Union has created incredible momentum for explainable AI as opposed to the other kind. The reason is because there's a 20 million euro fine if you're a European citizen and your decision is made by an automated system on your behalf which can't be explained. So there's a lot of motivation for explainable AI these days. And so with that as context, let me introduce my colleague friend, Andreas Holzinger. You see the affiliations, and he will give us his overview and then the relationship to medical explainability, and that will be the start of our fall series in explainable AI. Thank you.
Thank you very much. First of all, I would like to thank for the warm welcome here in Edmonton. I feel very comfortable, and I would like to present a few presents for my host. So this is the small one. This is for Melanie. Yeah, this is our logo, human-centered AI. And please, Melanie, this is a little present from Austria.
Thank you very much.
This is for you.
Unnecessary.
And the second is Husam. This is also a little one. Yeah. Where's Husam? Husam, thank you very much for your help.
Thanks.
And last but not least, for Randy, of course, and this is a large one. This is intentionally.
Unfortunately necessary.
It is a very large one because this is a coverage for his Audi TT. Thank you very much for hosting me.
If you expose this, I'll take pictures.
This is one of the disadvantages of cameras. They have to. Okay, ladies and gentlemen, I'm coming from Europe, specifically from Austria. It is not far away from Bavaria. And I'm from Graz and Vienna. So Vienna and Graz, these are the largest towns in Austria. And we have some specialities. One is that we have the honor to have the largest biobank of Europe. And this is a view to Graz that you can see it. The county is called Steiermark, and Steiermark has very much in common with Bavaria. And we have some guests from Bavaria also here. And this is our campus. This is Graz University Hospital, approximately 2,300 beds, and we have all facilities. So I have my group on this campus. So actually, we have our laboratories here. But I'm habilitated at the Technical University, and I'm teaching at TU. TU is short for Technische Universität, Technical University, at both Graz and Vienna. So this is part of our group. So you see, this is just for our Bavarian guest here. Okay, just that we have a common understanding in terminology. AI is really a very, very broad field, and I'm absolutely unhappy with the terminus itself, but it is here and it is a buzzword, but it is a very large field. The workhorse of AI is machine learning, as you all know, and one specific part is deep learning. This caused so much enthusiasm in the past, and this, to be honest, this is the reason why AI is so popular today. But we are going back to the roots, and Randy is one of the pioneers of AI. He did AI actually when nobody talked about it. Yeah? And now,
Just means I'm really old.
now, due to the success of these deep learning methods, we have a problem. And this is actually because we have just discussed with the camera colleague, we are flying to the moon, but we are mingling around with just cabling. So this is very interesting, yeah? So, okay, so what is the problem actually? These deep learning models, these neural networks are successful, of course, but they are very high dimensional. They are very non-convex. They are resource and data hungry, as you all know. But most of all, they are lacking interpretability. That means they are black boxes. And as Richard Feynman put it, we have discussed this recently, and therefore I have put this in now in the morning. Richard Feynman on the universe, it's not complicated, it's just a lot. And this is a very good comparison to the deep learning approaches. So, this is a very successful example of a recent work by the group from Sebastian Kroon in Stanford. And they had very much success in classification of tumors. But first of all, they need millions of data, 1.5 millions of data in this case. And the second is, they just can classify whether it is malign and benign, but they cannot answer why this is the case. And this is problematic because although we understand the underlying mathematical principles of such networks, we have a problem in retracing because it is just huge. It is so high dimensional that it is nearly impossible to debug it on demand. And this makes it problematic, and we call such approaches black box approaches, as you know, although this is not quite correct because a black box is something good which is in the airplane, yeah, but this is not this black box, yeah. And Randy pointed it out already. In Europe, we are a little bit more ahead of this problem because of this GDPR. So there is, since 25th of May 2018, a right for explanation. This is not a technical right, it is a juristical law to give every citizen of the European Union the right that you get an explanation on demand. Not on time, but for example, for a juridical case. And this now makes the work before this one problematic because now, if something happens, you can ask, why did the algorithm classify this as benign or malign? And this is a big problem because now you have not the possibility to retrace, to answer the question of why. Okay, and this is also a slide which I put in for Randy because he's mad on cars. And what worries me most is that these deep learning models, as beautiful as they are really problematic in certain tasks. For example, the result of a classifier of this was horse. And I'm asking the audience now, what do you think, why is this class has been classified as a horse? Melanie, what is your guess?
The logo.
Exactly, the logo, yes, this logo. This is a horse. And the classifier cannot determine the difference between this and this, makes it then a horse, which is totally wrong.
I'll trade you a horse for that horse.
Yeah. What worries me even more is that adversarial example can really very easily disturb these models. For example, you have this famous example with the panda, which is not very high confident that it is a panda, but then you have some salt and pepper noise, for example. You bring it in, and then immediately is a gibbon with 99.3% confidence. This is really a danger, really a threat, because this would be in the medical domain a no-no, an absolute no-no. And this is the motivation part for Randy's new laboratory. There's an urgent need for explainable AI. And this was the motivation now, and now I start with the real lecture. Okay. So, at first I would like to show you what is this human-centered AI approach, because this was developed by me for the last 15 years, so this has a history. Then I would briefly, very briefly show you the application area health. This will immediately lead us to probabilistic information. And then I will show you some examples of automatic machine learning, state of the art. And this will bring us then to the limits, and then immediately to where I'm pioneered in interactive machine learning with the human in the loop. And we will get to know how and why Randy is still important as a human. And I'm so delighted that so many humans are in here and not robots. So, this will bring us then to explainable AI, interpretable machine learning, and finally, I will show you some of our recent projects. This is called the KANDINSKY-Project. Okay, so what is this HCI approach? This is our old logo. You see the human, the H stands for the human, and this is the symbol for artificial intelligence, the old symbol. Of course, we do some algorithm development, but to be honest, to be really honest, we do 70%, we do data integration, data fusion, data mapping, because you need top quality paper if you do anything in machine learning. So the best algorithm will not perform if you have dirty, noisy, bad quality data. So you need high quality data. This is in the medical domain a must, but it is also important for any other field. And then at the end of the day, when other researchers go home, we have to continue our work 24 hours, because we have a customer, a demanding customer. This is the medical doctor. And the medical doctor is not interested in data. The medical doctor is not interested in algorithms. The medical doctor is interested to see something which can help him and make some decisions. So we have something to do to bring this in a very easy form in kind of decision support, visualization. And then all we do is privacy, data protection, security, safety, transparency, accountability, and ethics. And this is really very important for explainable AI, that with this topic we are very close to ethical, responsible machine learning. And this, I think, is in the future, in the next decades, the most important area to foster trust, for example, in this artificial intelligence. And then these are my private hobbies, so graphs, topology, entropy, a little bit of research here. So this cannot be done by one single person. It's impossible. Yeah? This cannot be done by a single group on this planet. This can be done only in a concerted effort, and therefore I'm very happy that we have a large international community, and our problem is internationally without any boundaries. So we work together with all parts of the world, and I'm very proud that I have 10 years ago, and Randy was the first who said yes, he's on board. Here we are. This is one of the first steps. We formed a large international expert network, and we have an own conference. This is called CD-Make. CD stands for cross-domain, to emphasize these combinations, because I'm convinced that in the combination of different fields we can do something new. And we do this year in Canterbury, Kent, UK. Last year, Randy were in Hamburg, Germany, and this is one of the pictures there where we had our sessions. And our goal is that human values are in line with to ensure responsible machine learning. So to combine this, and this is again a combined effort between this machine intelligence and this human intelligence. And this has a reason, because I have a PhD in cognitive science and I have a second PhD in computer science. So I understand these two worlds, and this is very, very important to put these two together because they can do a lot. So this is a proverb, and I always say this if I want students to engage for some work. I do not say this is my idea, I say this is the idea of Google. And this was also the idea of Google. Solve intelligence and solve everything else, but what do we need to reach a level of usable intelligence? Of course, we need to learn from data. We extract knowledge, and then we have the first problem, because generalizing is the hardest problem. This is tough. For example, guessing where such a probability mass function concentrates. And then we have a further problem, because the problems in the medical domain are mostly high-dimensional per definition. So we always have to fight the curse of dimensionality. And then we have to disentangle this explanatory, these underlying explanatory factors in the data. That means to understand the data in the context of an application domain. And I emphasize context because context is something genuinely human. To understand this context, and I will come back to this later, but our goal is not only understand intelligence, is a precondition, but our far-off goal is to understand the context in an application domain. This is not our goal, so we are not interested in this sort of intelligence, humanoid AI. We go towards human-centered AI, which is totally different. Okay, this is a typically set in the hospital, and this should show you the complexity of the application area health informatics. And the first question which you as the audience will have is, why is the medical domain complex? Who of you have worked together with medical doctors yet? Okay, Osma, of course, is an expert, but not so many. So I'm happy to show you a little bit the complexity of the medical domain. And this is actually a very old slide. The other slides were very young, produced this morning. But this is one of the oldest slides of me. And I was visiting professor at University College London with Anne Blandford. And I showed this slide when I had this first lecture. And I wanted to be very funny, so I showed on the one side the scientific branch or the scientific field of medicine. This is biology, physics, mathematics, chemistry, and so on. And on the other hand, we have this patient center, these doctors, these really practitioner clinicians. So we have here the research aspect of medicine and here the practical aspect of medicine. And I wanted to be very funny and show this picture. This is underground. So the London people have an underground. This is a tube. And yeah, and interestingly, Anne Blandford was sitting in front of me, and I clearly remember she went up and said, "No, there's no gap." And I was very, let's say, peinlich berührt. I did something wrong, maybe. And she continued and said, "There's no gap. There's a huge gulf, an ocean between those two worlds." Because as Osma, she has experience in working with medical doctors, and this is not easy. They will not come to your building. Yeah? You must make the first step.
We have some.
Some ladies are coming, of course. Yeah? Some medical doctors are coming, of course. But at this time, I formed the central hypothesis, and because doctors are not interested in data, of course. They are also not interested in this, what we call knowledge, because they have their own knowledge, and the good knowledge. But what they share is information. This needs both worlds, needs information. And I think the information quality is of utmost importance for that, and can maybe bridge this gap between those two to increase the quality of information, to help to make better informed decisions, for example. So decision support for the medical doctors. Yeah, and where's the problem in building this bridge? You see this bridge, this is also a brand new slide. So, okay. The main problems are heterogeneity in data. So you have a lot of contributing data. We have data integration, data fusion, data mapping, data cleansing, and so on is really very important tasks here. Fusing together these various data sets, then these are all in high dimensions. That means very complicated. This leads us to complexity, and then of course we have a lot of uncertainty, inherently uncertain data in the medical domain. This is the nature of medicine. And this brings us immediately to probabilistic learning, and here James Clerk Maxwell, the true logic of this world is in the calculus of probabilities. And this is my absolute hero, my historical hero. So my absolute hero is Randy Goebel, of course, yeah. But my historic hero is this man. Who of you, the young students, I have to look at the young students because this is my first question. Do you know this man?
Laplace.
Absolutely correct, Laplace. Normally, nobody does know that. Therefore, I give some hints. Probability theory is nothing but common sense reduced to calculation. This is the first hint. The second hint is this image, because everybody knows this girl. And this is Shakira. This is interesting. Yeah? And Pierre-Simon de Laplace, he was really the, let's say, the founder of the theoretical basics which we use now in the daily problem solving in machine learning. And actually it was Richard Price who published the posthum the work of Thomas Bayes. Everybody heard of Thomas Bayes, of course. But Pierre-Simon de Laplace put it in a mathematical form, and in a form which is readable, because if you read this original manuscript of Thomas Bayes, you get lost, you get immediately lost. And it is still known as Bayes' theorem. It is not quite correct. It should be maybe Price, Bayes, Laplace theorem. But how it is called Bayes' theorem. So we have this hypothesis. These are these uncertain quantities. We have the data. These are the measured quantities, the entities, and then we have a prior probability, and this is the most critical, of course, of these probabilistic approaches. Where does the prior come from, of course? So this is a very, of course, a problem. But then we have the posterior probability. That means the probability of an hypothesis given the data D. And this leads us to the base formulation. So we have the posterior is the prior times the data given the hypothesis, and then we have somehow we have to let's say to bring it to a factor which we can read. So to make a good assumption out of it. I give you an example. I can give you an example only in 2 dimensions, unfortunately, because of the limitations of this surface here. So here we have this feature parameter theta on the x-axis, and then we apply this, the prior probability, and we multiply it by the likelihood, and then we get a new posterior probability. And this works also in high dimensions very beautifully. And this is very, very good, and this is the essence of the success of today machine learning, because this works and this can deal with the uncertainties of the medical domain. The only problem, of course, is, and this is not only a tiny problem, it's a huge problem, is that this space is very high dimensional, so this rapidly becomes untraceable. And you would now ask, why is this relevant for medicine? This is highly relevant because in medicine we have exactly this. You take this patient information, for example, observations, symptoms, test results, omics data, etc., etc. And then you reach conclusions as a medical doctor. You predict the future. For example, how likely will the patient return to my clinic, to my department? How likely will the patient do that, do that? That means you always form a prior, the belief before making a particular medical observation, and then you conclude to a posterior, it means a belief after making this observation. And this is the prior, of course, for next observation, and this is intrinsically incremental. So you see, this is nothing else than the applied base rule in the medical domain, and this is done for a long time. This is something which the medical doctors do at any time. What is interesting for me as from the cognitive scientific viewpoint is that similarly we do make assumptions or we do make decisions from a cognitive viewpoint. Here you see this is the physical entities. These are the stimuli from outside the physical world. We have the world of the nebula of uncertainty here. You have the data sets here, selective attention. I can prove that, for example, now. You will look at me and not at the screen because now you have no information here, but the maximum information is here. I can do the counterexample. Everybody is looking on this complicated image again. So this is a proof that something which we call selective attention is working. And due to this perception, you form hypotheses at any time. Even at this very moment, you come up now with hypotheses, new hypotheses, and now you try to fit this into your world of hypotheses, if this fits into your knowledge, and then you select the best possible alternative which you think gives the best reward, and you try always to reduce this uncertainty. This is what we call also learning in the cognitive domain. And of course, this is very important, the feedback loop then, and you have always this nebula of uncertainty. This is very important. Okay, so the goal, as you can see here, is reducing uncertainty. We can do that, we do that implicitly as humans all the time when we make decisions, but we can do that in machine learning by additional data points, additional observations, for example, more data. The more data you have, the better you can reduce this uncertainty. But, and this is the big but, always you need high quality data. If you have wrong data, false data, this can be disastrous. This is very important. Yeah, this is to reduce the uncertainty. And this works well also in higher dimensions. For example, here, scaling to high dimensions, the holy grail in this domain. And there's a nice paper from Nando de Freitas group. He was in Vancouver, actually, and I think he is now in Oxford, but I think he's now also working with Vancouver again. And taking the human out of the loop, I have put that in red color because to emphasize this, the grand goal of them is to exclude the human, to do it fully automatically. And this is a grand goal, and this is a good goal because for certain tasks we do not need a human in the loop, of course. And this brings us to automatic or also autonomous machine learning. And the best practice examples of autonomous machine learning are, for example, recommender systems. Everybody of you has purchased on Amazon, and this works really. It's not a joke and not a joy example. Try to, for example, to purchase something. For example, here a circular glass cutter, which you need every day, of course. Yeah. Have everybody of you purchased a circular glass cutter? No? But you know what this is. Okay. if you purchase this and try it out by yourself, I didn't believe that Amazon is doing that. You get recommendations. It's very interesting, very interesting. Here's the Audi TT. I looked up in the morning for the car of Randy, and you can see Randy inside the car here. And autonomous driving, for example, is a beautiful example for the trade-off of human and machine, for example, at level 5, no driver, hands-off, driver off. Some times this would be nice, because last couple of months ago I went to Passau from Graz, yeah, and I was stuck in heavy traffic at this Autobahn from further on to Regensburg, and I would love to have such a level 5 autonomous vehicle, because I could have written a paper for Randy. Yeah? And this makes sense. Or for example, if I returned, I was very tired, I couldn't really drive, but I went on to come home, and then I went into a thunderstorm, and it was very strenuous to drive on. So I wish to have this automatic car, which surely drives better than me in these certain circumstances. Yeah? So this is a good example. Autonomous driving is not a bad thing, I think. Yeah? So there's autonomous flying, of course. This is relatively recent, these autonomous flight vehicles. But then is the problem, why did the car do that? Who is responsible if anything goes wrong? And there are dozens and hundreds of different autonomous applications which are working beautifully in various domains. But all this needs a lot of data. They are very data intensive, so big data is necessary for this automatic or autonomous machine learning. And here, for example, is the famous example where you needed 10 million images to safely discriminate a cat from a dog. Yeah? But sometimes we do not have this big data. For example, in my domain, the medical domain, we sometimes still have not this big data. Sometimes we have only small amount of data. We have rare events where we have no training sets whatsoever. And then we have always these NP-hard problems, for example, subspace clustering, which we do a lot, K-anonymization, which is a very important topic, and protein folding. Proteins are the building blocks of life. They are in nearly every application in medical domain, and this is really hard to do it. So sometimes we need a human in the loop, because humans are very good. And this brings us to interactive machine learning, because I'm a fan of the human. Also of machines, of course, we want to play, we are boys, of course, but we need the human. For example, we need sometimes a doctor in the loop, or a group of experts in the loop, or a crowd of experts in the loop, for example. We have done several research on this and proven the concept of interactive machine learning with the human in the loop on our domain, subspace clustering, K-anonymization, protein design. And why should you bring in the human in the loop? Because in these automatic approaches, you always have this generalization error. We wish to know the error, but often it's not possible. But now, we can, for example, let the medical doctor have a look at certain results, and that means that we have the generalization error plus the human experience, and that means that we bring in human intuition. And humans are very good intuitively, and they can very good estimate if a result is trustworthy or not. So the question, of course, would be now from your side, why is this human intuition so important? This is important because humans are very good in generalization, where our machines are bad. And they can understand, and I have highlighted here relevant, because relevant is a very, very important word. What is relevant? understand relevant representations, then we can find, or humans can find concepts. I will come back to concepts in the last part of this talk, in our Kandinsky-Project. Concepts between P of x and P of y given x, with the causal link between y to x. And this brings me to the work of Judea Pearl, who works on this causality. This is exactly our quest to answer the question, why? And children can often do that very good. For example, your granddaughters, you didn't teach them thousands or millions of examples of cats and dogs. And they can surely discriminate every cat from a dog. So children are very good in this, although this was a science paper. So with such a thing today, you can make a science paper out of it. But this is also hard for humans. For example, these are the dogs, not Randy's dogs, but this is very difficult to check whether this is a dog. Is this a dog or a muffin, for example? If I bite him, then he will bite me, possibly. Or this one is also very tricky to find out which one is a living animal, and the hardest is this one. This is also hard for humans, I admit. Of course, it's both hard for humans and machines. And there is a recent paper, adversarial examples that fool both computer vision and time-limited humans. But I like this one, time-limited humans. This is exactly the medical professional, time-limited human. Yeah, the state of the art is terribly terrible. So for example, this is the best current model of bringing up explanations, for example, to get the caption of an image, so to describe the content of the image, what is in the content, for example, here this one. And this is a group of Stanford, Fei-Fei Li and Andrej Karpathy. Andrej Karpathy is now, I think, at Facebook. Tesla, exactly. Yeah. A woman riding a horse on a dirt road. Yeah, okay, it is a woman maybe riding a horse on a dirt road. Yeah, okay. This one is even worse. An airplane is parked on the ground. Or this one, a group of people standing on top of a beach. If we would apply this in the medical domain, this would be disastrous. And this is the best current state of the art. So you see, we have still a lot of work to do. And this brings me to the methods, to the current state of the art methods of explainable AI. So, but why? Again, why? I think one of the most important aspects is to verify that our algorithms or our classifiers do their work as we expect. So because wrong decision can be costly and dangerous. This is number one. Number two, what I think is important is understanding the errors. If we would know what errors the algorithm is doing, then we could do further. And this is my special favorite because of scientific replicability and causality. The why is often more important than the prediction, because this is our profession as university teachers, to explain, to teach. And this is at the core of the human essence, that we want to explain something. So this is very important. So what methods are there? The oldest methods are gradients, of course. With gradients we can do a lot. Sensitivity analysis, for example, we perturb a model and we look how it reacts for this. This is a relatively old method. Störungstheorie in German, for those who are able to speak German, a lot among us. Decomposition, of course, relevance propagation. There is on pixel, layer, and deep data decomposition. I will show some examples later on. This is the group of Klaus Robert Müller, TU Berlin, working on it. Optimization, this is the famous LIME example, for example, the beta transparent approximation from the Charles Güstrin group. Then deconvolution, guided backpropagation, for example, model understanding. Feature visualization is one of those inverting the neural networks. And this is a most recent work from the Google group, from Kim, qualitative testing with concept activation vectors, decaf, and network dissection, for example, dismantling it and look into it. Okay, one example, gradients. This is an old technique, and this is relatively good working. And the idea is also to get some heat maps out of here. I can show this here. So with the gradients, you get some sensitivity analysis, and then you get some heat maps. And from the heat maps, you can at least highlight what contributed to a result. This is a first step, but I would say this is not yet exploration. I will come back to the full-scale explanation later on. But this is a good first step. Here, for example, you have a certain image, input image here, you check for the images, you have the classifier, now you check which contributed to make it up a cat. You can highlight this by this heat map. And you can, of course, you can calculate and determine the relevance. For example, like this, you can, for each node, for example, you can get back the relevance, but it immediately gets very complicated because no network is that simple as like in this teaching slide, okay? These are the teaching purposes, they are easy. The real world is difficult. But this is a possible solution. For example, you have the input, you have no idea what works on, forward pass, and then you do some relevance propagation, and then you see which nodes contributed much or most to the output, to the relevant output. This is a good first step. Or for example, data decomposition is also a good first step for looking, for example, how does it behave. So this is a recent work from Klaus Robert Müller. And this can be applied for image classification, for example. You get an input image, you get some local features here, and then you get a classifier output, and you can go back, and at least you can look up what contributed to this classification. This is a typical cat example. So there's a rule, no talk without any cats and dogs. So this is layer-wise. So the before mentioned were pixel-wise. This is layer-wise. This is the most recent method of the Müller group in Berlin. For example, you have these feature relevances in layers, the whole layers. And then this is the work of Google recently, concept activation vectors. But my comment would be that they call of a concept vector space, and this is a relatively, let's say, far away human approach, because I think that humans do not think in vectors. Yeah? So this is a little bit difficult, but it is a first step, and it is a good work, and it contributes to the international scientific community in a very well manner. So this is an example of how they, for example, do this, how they produce these heat maps, and then you can see what contributes most for this. And this was the first application in the medical area. This is, again, Klaus Robert Müller together with the Charité in Berlin. This is a famous hospital. We work together with them. And this is from histopathology. And for example, this helps the pathologists to determine what contributed most for the classification output. Yeah, and this brings us now to work. This is the state of the art. So we are not finished with this field. So this field is on the beginning. It's a very young field, and it is a very, let's say, field which needs a lot of work in the future. And towards human interpretable models, this is very important because the end users shall be able to retrace the results on demand. That means that the medical doctor is able to retrace on demand and can explain why a certain decision has been made and what contributed to these results, to answer this question of why. But I think this is now, I'm speaking as an engineer again, we engineers need to understand our own machine learning models and not tapping in a fog, in a nebula. So, and this is, I think, in the future, one of the most promising approaches to combine the success of statistical learning together with what we call ontologies. It's called sometimes knowledge graphs and so on. It contains domain knowledge, which is necessary because I emphasize again, correlation is not causation. This is very, very important. Most of my young students forget this. Yeah, they think correlation and causation is the same, but it is not. And therefore, this is a very interesting work, for example, where you have each node of this network here, of this, you can see this decision tree structure is annotable. You can annotate it and you can bring in knowledge from outside, for example, human expert knowledge or knowledge from an ontology, but this has not been done yet, so this is cutting edge. There is no work to date which combines these statistical approaches with ontological approaches, and this would attach semantics to AI, so this would bring together the classic AI approaches, the logical approaches together with the statistical approaches. For example, we have this, let's say this medical image here, and we let it into a network, and we have a classification result, whatever, and then we want, and we can with the heat maps highlight already this, but what we need is an explanation, for example, why this is a tumor. And this means to describe the visible phenomena, for example, that it is a nucleus and that it has a void shape and circumscribed border, for example, which makes a malignant tumor in this case. Yeah? And this is a feedback loop, and this needs a human for check this plausibility. And but here, for example, we have these terminologies. We have developed a large pathological, so a large ontology for pathology. And here we could bring in this knowledge into these nodes to make them annotatable. So for example, that it brings out, this is classified as whatever because of nucleus, a void shape, circumscribed border, and so on, which would not be possible otherwise. So this would then really, this statistical model bring together with the classical knowledge graph ontology approach, and this would make, for example, easier generalization, but most of all reasoning, validation, and context. We could figure out the context of a particular medical problem, because this is always different. There is no single solution on this and no golden rule. This is very, very adaptive. So, and moreover, we can use it to analyze the internal structure. We can describe the networks. We can, for example, filter nodes. So, but this has not been done. So this is our next step. So, and now I come to the end of the talk, measuring machine intelligence, our Kandinsky-Project. So this was stimulated by the work. We have a long term cooperation with pathologists, and I always observed the pathologists how they work, and what comes into consideration is that they describe patterns. For example, there are objects, for example here this is a portal field, and there are several objects, and if this is in a group together in this shape, then it is saying something to the medical doctor, whether it is malign or benign and so on. And he describes this. He does pattern recognition, pattern understanding, and then pattern description. And interestingly, this histopathological image is a contribution, but legally binding, and therefore I admire the approach of Randy to include legal aspects in this. Legally binding is the text, this is natural language, this is the communication part, this is legally binding, and this is text, and this is hard to process for computers. And this brings me back to a very old work from David Hubel and Thorsten Wiesel from 1962, who figured out that the world is compositional, and the networks today, the deep learning networks also work kind of that they composite and build these compositional objects together from simple ones to more complex one, and then you have a concept out of this, okay? And I was also inspired because I like art. I always visit art museums, and there was a Russian and later French artist who was called Wassily Kandinsky. He lived from 1866 to 1944, and he had a certain art. You can see these shapes of these circles and these triangles and so on. And this inspired us to do the same for the machine learning community. And we have now built on GitHub a Kandinsky generator who can, in a certain, very specified environment, produce patterns. And we can use these patterns now for two purposes. First of all, we can check, or we can challenge the machine learning algorithms for bringing up answers to it in plain natural language, in text, but also we can understand how humans operate with such Kandinsky patterns. For example, if we look at the A, what do you think, which concept would behind this first pattern here? Look at these four figures. This is a Kandinsky figure here. Figure 1, figure 2, figure 3, figure 4. This forms a pattern. What does this pattern contain as concept? Husam, what do you say?
These are negative examples?
Yep.
So it's a set of blobs, circles, squares, and triangles.
Yes,
And
yes.
what's the concise one and what's the simplest one? Or
Yeah, it is. Here is the color, for example. They are all the same color. Color is here.
you
And
don't have any negative examples.
pardon?
You don't have any negative examples.
There are no negative examples. I come to the negative example later on. But interesting, color has is very important in histopathology. So the color has of the staining and so on has a very strong, let's say, impact on the decisions. This is, for example, color. In this one, what do you say is in this the concept? Shape, absolutely correct. Yes, shape. This was easy. And in the last one, pardon? Quantity. Simple, the amount of objects in the image. Yeah? But there are, of course, there would be more hypotheses possible. For example, here in this, you have the arrangement. For example, this is in the edge, in the corner, for example. Or this is in this part of the figure, and so on. Or here you have Gestalt principles. So from psychology, there are known Gestalt principles, so that certain objects grouped together have certain psychological impact on the perception. So this is this Gestalt principle. And then you have domain knowledge. What do you think is the domain knowledge in here, in F? Your botany, yeah. Flowers, exactly. This is the domain of, for sure, are flowers. For us, these are flowers. Exactly. Now, I'm really curious if a machine can detect this and can, for example, give an explanation what it is. And here, for example, this is the pathology challenge. This is a true pattern. So, for example, this has a meaning. The pathologists know what it is. This is a false example, so this is random, and this is the counterfactual. This is exactly the opposite of this one. So this contains a pathological proven concept. And here, this is one, I have this also printed out. So Randy has the file, and you can download it from the Twitter account, from my Twitter account. So to be honest, I'm not a fan of Twitter, but my students have urged me to use Twitter. They say, yeah, every professor should use Twitter, blah, blah, blah. So yeah, of course. So I listen to my students, and now I use Twitter. So, and there's the Twitter address on this, on top of the presentation, and you can download this booklet. This is a Kandinsky booklet. This is for testing humans, for example, so for finding out which hypothesis humans follow. And we contrast this, or we want to contrast this then with machine algorithms. And the idea is the following. Here you have the pattern. These 16 images contain the pattern. All figures of this belong to this Kandinsky pattern. And this is the counterfactual which Russ said is the counterfactual. This is not part of the pattern, meaning none of the figures belong to this Kandinsky pattern. Now, what do you think? Is here the leading hypothesis? You can say it.
Red color.
It contains at least a red object is the correct answer, exactly. It only contains circles and triangles, would be a hypothesis, but not a full true hypothesis. This would be the full true hypothesis. It contains at least a red object, at least one red object.
This is one hypothesis.
This is one hypothesis, exactly. Yeah? There are, of course, often many various hypotheses, and we are curious about the creativity what humans bring up on output. But the goal is, at the end of the day, in our project, that we have a whole slide image from a histopathological slide, and we feed this slide into our algorithm, and a description comes out what is in the image. And this is the example for doing fundamental research, because this is controllable and we can generate all sorts of patterns, and we have no noise in it, because in the histopathological slide in the real world you would have a lot of noise, disturbances and so on. Okay, now this is your part. What do you think is here the leading hypothesis, or one of them? What do you think?
I have a question about the last one.
This one.
It's actually about all of them. When you think about being able to formulate hypotheses, there's a threshold of complexity where most humans won't be able to form a hypothesis that covers, but that partially covers, for example. And that's probably relevant in the subsequent.
Absolutely. Yes, yes. Yeah, yeah.
And that threshold
I agree.
can only be determined, I think, empirically, right?
Yes.
And it's related to the difference between the quality and alternative explanations.
Exactly.
As well.
Yeah, absolutely correct. Yeah. Yeah, this is fundamental research in our project, and we are just starting the experiment. So you are the first guinea pigs who see that. Actually, yeah. This on Randy's printer, the first booklet came out. Yeah. So this is historically, in 20 years, you will say, yeah, the origin was in Edmonton. Okay, what do you think about that?
Four.
Exactly. All of the same shape, all objects have the same shape. Don't be distracted by the colors. For example, all have the same shape. Or this one. This should be easy for people from the United States of America. This is a hint.
Oh, yellow is the center of the universe?
Yeah, could be. Look at this shape. I'm curious. My wife immediately spotted that. Yeah, all the others she found very difficult, but this she spotted immediately. She found immediately the correct answer. Yeah? Now I'm really curious if anybody in this room finds out what is the only true hypothesis behind this. What?
There are three parties in the US, red, blue, and I guess the yellow one is third party.
Okay. He thinks very complex. Very complex. Exactly. Bravo, Mickey Mouse. Mickey Mouse. Every figure contains a pattern which is made out of a big yellow circle. You have determined that, and two smaller blue ones, and looks like a Mickey Mouse. This is domain knowledge. Only if you are a Disney reader or whatever, you know that. Yeah.
I thought it represented volume of idiotic tweets. Like the another hypothesis. Yeah.
Yeah, and now you can take part in the